Hello friends. Now the third circuit in general linear applications of op-amp is difference amplifier. In this configuration, in this amplifier, we give input to the inverting terminal, which is having negative feedback, as well as non-inverting terminal. Fine. But there is a set of assumptions. What are those assumptions? Op-amp is ideal. This operational amplifier is ideal, and if this is ideal, so biasing current entering at inverting and non-inverting terminals is 0. Fine. And we assume these are two nodes. So the procedure of analysis of any operational amplifier circuit is, I repeat it again, first find the voltage at non-inverting terminal. Find the voltage at non-inverting terminal. For ideal op-amp, voltage at inverting terminal is same as voltage at non-inverting terminal. So we will take this voltage same as this voltage and then apply KCL at inverting terminal. This is the procedure of analysis of any circuit based on operational amplifier. You should remember the procedure. Fine. So now apply what is voltage at node B. Voltage at node B. Please see, if current here is 0, current entering into non-inverting terminal is 0 for ideal op-amp. So voltage at node B is nothing but voltage across this resistance, and voltage across this resistance is what? R3 divided by R2 plus R3 into V2. That is called voltage divider rule in network circuits. So voltage at node B is obtained by applying voltage divider rule, that is R3 by R2 plus R3 multiplied by the voltage V2. This is known as voltage divider rule in circuits. The voltage across this resistance is what? This resistance divided by sum of 2 into this. Fine. So we have obtained voltage at node B. Now for ideal op-amp, we have already seen the voltage at inverting terminal is same as voltage at non-inverting terminal. Therefore, this must be equal to, that is R3 by R2 plus R3 multiplied by voltage V2. So we have obtained voltage at node B first, and then we have said the voltage at this node is same as voltage at this node. This is the general procedure of analysis of any op-amp based circuit. Fine. Now apply KCL at node A. When you apply KCL at node A, this voltage minus this voltage divided by this resistance is current going this way. So that is VA minus V1 divided by resistance R1. This is outgoing current from node A. Then this voltage minus this voltage divided by this resistance is outgoing current from node A, that is another resistance. So VA minus V0 by RF is resistance which is going towards V0 in resistance RF, and current entering at this terminal is 0 for ideal op-amp. So this is equal to 0. Fine. You can write the expression directly like this, or you just by that is just modification of this, that is V0 equal to minus RF by R1 into V1, this voltage, right, plus 1 plus RF by R1 into VA. Fine. So if there is some voltage at this node, I can write the expression directly, that is V0 is RF by R1 into Vin. V0 is minus RF by R1 into V1 plus 1 plus RF by R1 into this voltage or this voltage, that is same thing. Fine. That is just simplification of this expression only. So this gives the output voltage equal to minus RF by R1 into voltage V1 plus 1 plus RF by R1 into this voltage. Why? Because VA is VB. VA is VB, and that is nothing but R3 divided by R2 plus R3 multiplied by voltage V2. This is the expression of output voltage of this circuit. Fine. Now, there has to be some alterations for this circuit to be the difference amplifier. Difference amplifier means it should be able to amplify the difference of these two voltages. I say this is plus, not this plus. This is non-inverting, so I'll say this is plus, this is minus. So I will say difference of these two, that is differential input, is nothing but V2 minus V1. That is my assumption. I am using this circuit as a difference amplifier, difference of input voltages. And I will assume the voltage connected at non-inverting terminal is positive, voltage connected at inverting terminal is negative. So difference of these two is what? V2 minus V1, that is VD. So I will be amplifying that difference. Only then this circuit will be acting like a difference amplifier. Let us see the alteration. I have to make, what is the purpose here? I have to make gain of the circuit same for V1 as well as V2. How to make it? Gain with respect to V1 is what? RF by R1. Gain with respect to V1 is what? RF by R1. I have to make gain with respect to V2 same as RF by R1. I have to make this as RF by R1. How can I make? Let us see that. I will modify this equation. Let us see the expression. V0 is equal to, I can modify this a little bit, minus RF by R1 multiplied by V1. Now simplify that. R1 plus RF divided by R1 multiplied by R3 by R2 plus R3 multiplied by V2. I repeat, I have to reduce this factor same as this so that I can amplify the difference. So that I can take that factor or this factor, if both are same, I can take that as common out, right? Let us see. If so, to make it this, please see that to make it RF by R1, I have to make it RF by R1. So R1 can be taken outside. R1 can be taken outside. And if I make it RF, R3 is equal to RF, make R3 equal to RF. Make R3 equal to RF and make R1 equal to R2. I repeat, please understand this concept. I have to reduce, this was the expression, R1 plus RF by R1. I have to make this factor same as this factor. So how can I make? Please see it carefully. If this is same as this, and this is not RF, rather this is, please see that carefully, this is R3, I'll rewrite that expression, R3 by R2 plus R3, this. So I have to make this RF same as RF by R1. How can I make this R3 as RF, make R3 same as RF? So I will say let R3 is RF. I will select this resistance same as this resistance. 1, 2. Now for making this factor to be same as this, I will say this is R1. So I will select R2 is same as R1. Fine. In that case, this and this is cancelled. So what do we get? So I will say, so I will modify this equation like this. This is RF. This was R3, this was R2, this is R3. So I will say if R3 is equal to RF and R2 is equal to R1, if this is same as this and this is same as this, then let us see the expression. V0 will be equal to what? Minus RF by R1 into what? Into V1 plus, see this now, R1 plus RF divided by R1 into R3 is what? RF R3 is RF. R2 plus R3 is what? R1 plus RF. So R1 plus RF into V2. So this and this is cancelled out. So V0 will be equal to minus RF by R1 into V1 plus RF by R1 into V2. Or I can say this is equal to RF by R1 into V2 minus V1. Why? Because it was negative. So this is what I have. So this gives what? This gives AD into VD. Where? What is AD? Where AD is nothing but RF by R1. You can say this is differential gain. That is what? Differential gain of this circuit. And what is VD? VD is differential input or difference input. VD is what? A differential input. That's it. I hope concept is clear. Fine. Now try to recall differential amplifier. This circuit is acting like a differential amplifier. In differential amplifier we have two types of inputs. One is called differential mode input, that is V2 minus V1. Another is called common mode input. So for common mode input, what do? We connect same input to both the terminals. In common mode inputs, we connect same input to both the input terminals. That is called common mode input. If V1 is equal to V2, that is VCM. If V1 is equal to V2, that is VCM. V1 is equal to V2. V1 is equal to V2 and that is equal to VCM here. So this difference will become 0. And if this difference is 0, so what will be output? Output of this circuit will be 0. That's what I'm trying to say. If this condition is satisfied, if R3 is RF, R2 is R1. If R3 is RF, R2 is R1, this is the circuit. In that case, the output for common mode input is 0. And if output for common mode input is 0, what will be the common mode gain? Common mode gain will be 0 because this will become 0. So what I mean to say is the common mode gain for this circuit is 0. Why? Because output is 0 for non-zero input. If output is 0, so that means there must be 0 gain, common mode gain. So for this circuit, for the, what do we have? Common mode rejection ratio is nothing but differential gain by common mode gain, and that is AD by 0, and that is infinite. So for this particular circuit, your common mode rejection will be 0. This is differential circuit using op-amp. This is differential amplifier using op-amp. Earlier we have talked about differential amplifier using BJT, differential amplifier using FET in chapter of differential amplifier. This is differential amplifier using op-amp. And for differential amplifier using op-amp, common mode gain is 0 by selecting RF equal to this resistance, R1 equal to this resistance. And that circuit has infinite common mode rejection ratio. So sometimes we make use of this circuit as differential amplifier. Fine. So now there are few more points to be discussed here, but remember this circuit is very important for all the exams. You will find a lot of questions based on this circuit, that is nothing but difference amplifier. This circuit is what? Difference amplifier. But there is special case here. There is special case what? If we have V2 equal to V1, sorry, not V2 equal to V1, if RF is equal to R1 and that is equal to R2 equal to R3, it means all resistances are same. Fine. If all resistances are same, in that case this gain will become 0. In that case differential gain will be not 0, 1, sorry. So output of the circuit will be V2 minus V1. That is what? Subtractor circuit. That is what? Subtractor. So for subtractor, all resistances are kept same. These resistances are kept same. Fine. There is another condition for subtractor circuit. We can see that later on. I have to select proper values of R1, RF and these resistances, but by selecting suitable values, I can make output as difference of two input voltages, that is nothing but subtractor. So I can make use of this circuit as subtractor circuit. Fine. Similarly, the same amplifier, which is difference amplifier, can be used in other ways as well. What are those? That is single-handed input, double-handed input. The subtractor, single-handed input means what? It can have different modes of operation. Your difference amplifier can have different modes of operation. First is differential mode, where the both voltages were different. This was different in comparison to this. So VD was V2 minus V1. That is called differential mode of operation of this circuit. Another possible case is I have same input voltages. Here what? Both voltages are same. That is called common mode input. VCM. VCM can be, we can say V1 is equal to V2. That is called common mode input for this circuit. Third mode can be differential mode, right? In differential mode, I have V1 equal to V2, and you can make this like this also, V1 equal to V and V2 equal to minus V, or V2 can be equal to V and this can be minus V. Fine. In that case, what will be the gain? This condition will be kept same. So output will be equal to RF by R1 into V2 minus V1. V1 is minus V, so that is RF by R1. V2 is V and V1 is minus V, minus of V. So this will be what? This will be 2RF by R1 into V. Or basically in that case what? VD is what? You can simply say VD for this circuit will be what? V minus V, that is 2V. So that is 2V input. VD will be, or we can say like this, this is 2VD. That is called differential mode of operation of difference circuit. So your difference amplifier can work in differential mode, it can work in common mode, or it can work in single-handed mode. What is single-handed mode? I can make this to ground, apply input here, that is called single-handed input. I can connect this to ground and apply input here, that is single-handed input. And those are the examples of inverting and non-inverting configurations, inverting and non-inverting amplifiers. Fine. So this is all about your difference amplifier. Now we will see the examples based on difference amplifier.
Now let us see the examples based on the difference amplifier. Here the first circuit is, that is a single op-amp with the difference input voltage applied. At inverting terminal we have 2 volt applied, and at non-inverting terminal it is 3 volt. So we have to find the output voltage of this circuit. So here remember, in any operation amplifier circuit, the procedure is you first find the voltage at non-inverting terminal and then apply KCL at inverting terminal. So the voltage at non-inverting terminal VB will be the voltage across 8 ohm resistance. So that will be 8 divided by 8 plus 1 into 3 volts. So this is voltage divider rule. The voltage at node B is 8 by 3 volt. Now to find the output voltage, apply KCL at node A, that is the inverting terminal. So when you apply voltage at KCL at inverting terminal, so we have current going in this branch is VA minus 2 divided by 1 kilo ohm, then VA minus V0 divided by 5 kilo ohm. The sum of outgoing current is 0 because current in this inverting terminal is 0 for ideal op-amp. So the sum of both currents going away in this direction and going away in this direction is 0, and that gives the expression of KCL. For ideal op-amp, the voltage at node A is same as the voltage at node B. You should remember that. So here we have already obtained voltage at node B. So voltage at node A is 8 by 3 volt. So by putting this voltage VA here, you get output voltage equal to 1 plus 5 by 1 into VA minus 5 by 1 into 2. That is simplification of this equation, and that gives the expression of output voltage. Fine. So we have applied voltage at both inverting as well as non-inverting terminal, and we have calculated output voltage. So that is 6 volts. So 6 volt is option B in the question. That was GATE EC 2003. Now the differential input resistance of the circuit shown in the figure is, you have to find the differential input resistance. So what is the meaning of differential input resistance? So differential input voltage to this circuit is what? V1 minus V2. So here what we do, see it carefully, in this circuit we have, that is simple difference amplifier. So here the differential input to this circuit is what? That is the difference of these two voltages, and the differential input to this circuit is, that is nothing but V1 minus V2, right? And current in this branch is, suppose I, you can take incoming or outgoing. So here I will be assuming that is like this. So there is a little correction, although you can take either of the direction. Fine. So now I have to find VD upon I. So that VD upon I, that is differential input resistance of this circuit, will be VD upon I. So I have to find this ratio. Fine. So let us see the expression. So the procedure for this circuit will means my aim is to find out the ratio of VD with the current of the circuit. Fine. So here voltage at node B is what? That is nothing but voltage across this resistance RF. In terms of V2 we will be finding, so RF upon R1 plus RF into V2. RF by R1 plus RF into V2, that is voltage at node B. So this is as per voltage divider rule. So voltage at node A will be same as voltage at node B for ideal op amp. So VA is equal to VB, that is RF by R1 into V2. Fine. Now what is current supplied by the source? So here I am taking just this is positive, this is negative. So direction of current has been taken, that is nothing but going away from terminal A. So that is the express direction of current I have taken, like that. Fine. So I will be taking that same direction initially which was given in the circuit. So VA minus V1. VA minus V1 is nothing but VA minus V1 will be current in this direction. Remember this. Fine. VA minus V1 by R1 is current in this direction. So VA minus V1 by R1. VA we have already obtained. So VA minus V1 upon R1 will be this expression. So for differential input, remember one thing. For differential input, what we assume, V1 is equal to VD by 2 minus, and V2 is equal to VD by 2. Fine. So that is what we assume. Differential input is, for differential input, this is taken to be positive, this is taken to be negative. You can take it like that. Fine. V2 minus V1, that is V2 minus V1. So we will be changing the polarity of this voltage like this, that is plus, this is minus. Fine. That is the little change in the polarity here. So V1 is negative, V2 is positive. Fine. So the current I will be, you can replace V1 by minus VD by 2, V2 by plus VD by 2 in this equation, and you get the expression of current I. And we know VD by I. So you find the ratio VD upon I, that is equal to, simplified expression is this. And since our feedback, that is RF, here we will be assuming that R1 plus RF is almost same as R1 plus twice RF. So this will be approximately equal to twice R1. So the differential input resistance of this circuit is twice R1. So there was little confusion about this part. So I will just rectify this particular issue here. Remember, differential input voltage of op-amp is nothing but, that is differential input voltage at non-inverting terminal minus voltage at inverting terminal. So that means V2 is positive and V1 is negative, and in that case current will be entering from V2 side and it will be leaving from V1 side. So that's why, so there will be little change in this polarity. So this should be minus, this should be plus. So that was the polarity which was creating that confusion. So that is one correction in the solution of this question. Otherwise the expression of the differential input resistance is twice R1 only. Now let us see the next example. In the circuit shown in the figure, the op-amps used are ideal. The output voltage of the circuit is. Now please see this circuit carefully. You have to find the output voltage of this circuit. So this is basically the cascade connection of two circuits of op-amps. See carefully this circuit. This second part, that is output stage, is nothing but non-inverting configuration. Fine. And input part, this input part is nothing but a differential configuration or difference amplifier. Fine. And when all resistances of the difference amplifier are same, this RF is this equal to this resistance, R1 is equal to this resistance. If all this and this and this and this all resistances are same, then the output of first stage, suppose output of this first stage V01, I will say V01 is equal to the difference of input voltages, that is V2 minus V1, and I will say this is V2 and this is V1, so that is equal to 2 minus 1, that is 1 volt. Fine. So that means output of this first stage is 1 volt. So if you consider that is nothing but input to this non-inverting configuration. So the output of non-inverting configuration is what? Output of non-inverting configuration is given by 1 by RF by R1 into nothing but input to the non-inverting configuration, that is the output of the first stage. RF here, I'm saying this RF is this resistance, R1 is this resistance for the output stage. So this is 1 plus, that is 1 by 2 into output of the first is, that is this. So this is nothing but 1.5 volts. So answer is this. So I'm not going to the solution. Solution will be a little more explained, but I have given you the output. Fine. So that is how you do. Now let us see the next example. The output of the op-amp in the circuit shown in the figure is, you have to find the output of the circuit. See this circuit carefully. All resistances this that are same, and input to this terminal and input to this terminal. Say this is V2, this is V1, right? Say this is V1. So what will be output? Output of the circuit, this is nothing but simple difference amplifier, and that is nothing but V2 minus V1. But here V2 and V1 both are same because it is shorted and given connected at 3 volt. So that is 3 minus 3. So this is 0 volt. So you can see this. So this is 0 volt. Answer is A. So that is explained here. I have given the complete solution, but right from the initial stage itself, if you see the circuit, this is what circuit? This is simple subtractor circuit, you can say, that gives the difference of the two input voltages when all resistances are same. So by seeing the resistances, or by just having look at the resistances, if all resistances are same, the output of the circuit is difference of this voltage and this voltage, but this is 3 volt itself, both are same, so output is 0. Fine. Now let us come to the next example. The figure shows a single op-amp differential amplifier circuit. So this is differential amplifier circuit only, and which one of the following statements about the output is correct? So you have to identify which one is correct. Fine. So the procedure remains same. What is the procedure? Find the voltage at in any op-amp circuit. If nothing is clear to you, what you do, you find the output, you find the voltage at non-inverting terminal first, and then find the voltage at inverting terminal. But here there is a little confusion about polarity. It is plus, given to be plus, and it is given to be minus, but if it is a feedback circuit, the polarity should be other way round. Remember, the feedback is always given at negative terminal, so this should be at minus terminal. Fine. So now you can see here in this case, when you find the output voltage with this correction in the circuit, this is one correction I have made in the circuit, assuming that feedback is at negative terminal. So rather than going into the original question, this is there. But of course, you can go to the original question as well. You can refer that, but I'm assuming that we have negative feedback. So when there is negative feedback, what we do, we find the voltage at node B, that is at non-inverting terminal, then apply KCL at inverting terminal. That procedure remains same for all the circuits of operational amplifier. So there should not be any confusion about the procedure. So find the voltage at node B. Voltage at node B is obtained by simply applying the voltage divider rule, and you have seen examples earlier. This will be this resistance divided by this plus this. So this divided by sum of this resistance, this and this. Fine. So that is sum of these resistances. So VB comes out to be 18.17 volt. For ideal op-amp, voltage at node A is same as voltage at node B, because voltage at inverting terminal is same as voltage at non-inverting terminal. So voltage at node A is 18.17, that is same as VB. Now apply KCL at this node. So VA minus 10 divided by this resistance, that is nothing but, you can find, that is 10.5 kilo ohms. I'm writing this in kilo ohms. Then VA minus V naught by this, I'm taking V naught, so let it be V naught here. Fine. So what we do, that will be nothing but, that will be giving me the output voltage. That is, you can simplify this expression by replacing VA by this 18.17. So you get the output voltage to be 95.975, and you can see the options. So that is this one, which is giving me correct answer. Fine. So now let us see the next example. For the op-amp circuit shown below, the output is approximately equal to, so you have to find the output voltage. Fine. At the output terminal. So the procedure is again same. What we do, find the voltage at this node, find the voltage at this node, then find that voltage at non-inverting terminal, and find the voltage at inverting terminal. That is the procedure. So what is voltage V2 and V1? So you simply apply the voltage divider rule. So V1 is what? Voltage across this resistance. So that is 105 divided by 105 plus 95, 200. So that is this voltage. What will be V2? This resistance divided by sum of these two into 10 volts. So that is this voltage. So we have obtained V1 and V2. So next step is find the voltage at non-inverting terminal. That is the simple procedure for every op-amp. So find the voltage at non-inverting terminal. So that comes out to be this much by simply applying voltage divider rule. How? This resistance divided by sum of 2 multiplied by V2, and V2 we have already calculated. So this gives me the voltage at node B. For ideal op-amp, voltage at inverting terminal is same as voltage at non-inverting terminal. So V minus is V plus. So VA will be equal to VB, and that is what we have calculated. And then again, just like previous cases, apply KCL at this node. So that gives VA minus V1. This voltage, VA minus V1 by 100, then VA minus V0 by 1 mega ohm, that is equal to 0. So what you do, what we have converted this into mega ohm. So that resistance which was here 100 kilo ohm becomes 0.1 mega ohm. So that is what I have done. Fine. So that gives me the expression of output voltage. So by simply putting VA from this expression here, I get the output voltage, that is equal to minus 5 volt. You can verify, you can simply apply these procedures or rules to the circuit. Whenever you find the voltage, output voltage, what you do, you find the voltage at non-inverting terminal, then apply KCL at inverting terminal. That is the procedure for every op-amp circuit, whatever is the type of circuit. Fine. So let us come to the next question. The common data for examples 33 and 34. Our differential amplifier is constructed using ideal op-amp as shown in adjoining figure. The values of R1 and R2 are given to you, and then what are the questions? If the input impedance seen looking into V1 and V2, that is differential input resistance, we have to find. That is one. Fine. Then you have to find your in next case we will see we have to input impedances seen looking into V1 and V2 with respect to ground. Fine. So that means if you see from here, what will be the input resistance, and if you see from here, what will be the input resistance. So you are, if when you look separately from this, so you put this to the ground like this, and when you see from this, you connect this to the ground. So you have to do it one by one. So input impedance with respect to V1. So when you find input impedance with respect to V1, connect another terminal to the ground. So if it is grounded, this is grounded, so voltage at node B will be 0 because current entering into this terminal or this terminal is 0. So if current here is 0, so current here is 0, current here is 0, VB 0. If VB 0, so VA will be 0. Remember, because for ideal op-amp, voltage at node B is same as voltage at node A. That is, voltage at inverting terminal is same as voltage at non-inverting terminal. So here VA will be equal to 0. So to find current in this branch, what do we do? VA minus V1 upon R1 will be current. So that is V. If you take incoming current like this, in that case, that will be V1 minus V. Why? Because you can simply see, if this is voltage V1 connected at non-inverting terminal, so what will be the resistance seen by the voltage V1? That will be nothing but V1 upon this current. Fine. Because this is already connected to ground, so I1 will be V1 minus V upon R1. So V1 is given to you. VA is 0 because this was 0. So I1 is V1 upon R1. So what will be the V1 upon I1? That will be equal to this resistance. You can see V1, I1 can be taken on this side. So V1 upon I1 is this, that is 47 kilo ohms. So if you see the resistance seen with respect to this terminal is 47 kilo ohms. So resistance with respect to V1 is 47 kilo ohms. And to find resistance with respect to V2, what do we do? Connect this terminal to the another terminal to the ground, apply voltage here, and the ratio of V2 upon I2 will be the input resistance of this circuit. Remember, this current will be flowing from here and that will be going to the ground, because current entering into non-inverting terminal of ideal op-amp is 0. So what will be V2 upon I2? V2 upon I2 will be total resistance seen by this path, and that is R1 plus R2. So ratio, the resistance with respect to V2 will be R1 plus R2. So that is 47 kilo ohms plus 470 kilo ohms. So you please see the resistance is given to you. R1 and R2 are 47 kilo ohm and 470 kilo ohms. So our resistance with respect to V2 will be R1 plus R2, and that is nothing but 517 kilo ohms. So that is what you have calculated. Fine. I hope the concept is clear and your expression final value of the output is clear. Final value of the resistance is clear. Now second part of the question, V1 and V2 are connected to voltage sources having an open circuit output of +1 each, and internal resistances of 13 kilo ohms and 3 kilo ohms respectively. The output voltages, you have to find output voltages. V1 and V2 are nothing but 1 volt each. Fine. But internal resistances of source 1 is RS1 is 13 kilo ohms and RS2 is 3 kilo ohms. So this is what you have done. and then you have to find the output voltage. Remember, for this circuit procedure remains same. Find the voltage at this node, that is non-inverting node, then apply KCL at this node, you will get output, and I have already explained a number of times in earlier examples. So output voltage, I have written the expression directly, you can do it yourself, and final output of this circuit comes out to be 0.15 volts. You should try it yourself. I have already explained the procedure. Fine. Now let us see the next example. In the ideal op-amp circuit given in the adjoining figure, the value of RF is varied from 1 kilo ohm to 100 kilo ohm. So this is the variable resistance in the circuit which is being varied from, that is 1 kilo ohm to 100 kilo ohm. The gain V naught upon Vi will be. You have to find the gain V naught upon Vi. Fine. Now let us see the output. Remember, this is, you are applying the same input at this terminal, you are applying same input at the non-inverting terminal. Remember, current in this branch is 0 because current entering at non-inverting terminal is 0. So whatever is voltage here, that will be same as voltage at this node. Fine. And the expression of this is nothing but with respect to this voltage, that is minus RF of R1, and remember with respect to this voltage, that will be 1 plus RF by R into Vi. So this is the expression of output voltage. Remember, you should remember such type of expression directly. Output of an op-amp circuit with negative feedback with respect to voltage connected on inverting side is minus RF upon R1, and with respect to voltage at this node is nothing but 1 plus RF by R1 into this voltage, that is this voltage. Fine. So that is the expression of output you get. As for the circuit, R is, when R is 10 kilo ohm. Fine. When RF is 1 kilo ohm, you get the output. When RF is 100 kilo ohm, you get the output. So in both cases, it is 1 volt. So output of this circuit remains 1 volt in both the cases. So that means it is independent of the value of RF. Fine. Now let us see the next example. In the circuit below, the operation amplifier is ideal and V1 is 10 millivolt, V2 is 50 millivolt, and the output voltage V out is, you have to find the output voltage. And I have explained the procedure. This was in GATE 2019. And if you are expert now, what will be V output? First of all, with respect to V1, that is what? 100, right? I will write it again. That is 100 by 10 with negative sign outside multiplied by V1 plus, what is voltage at node B? That is VB. So that will be 1 plus RF is 100, R1 is 10 into VB. What is this RF and R1? That is, this resistance is RF. I am saying this resistance is RF. This is R1. Fine. So if you know the voltage at node B, this is the expression of output voltage, and you should remember directly. Fine. That is the expression of output voltage. Fine. So now, how to find VB? VB is obtained by simply a voltage applying voltage divider rule. So that is 100 ohm. That is this resistance divided by sum of these two. That is 110 multiplied by input voltage. That is V2. So you can replace this VB by this expression. Fine. And V1 and V2 are given to you. So by putting those values here, you get the output voltage. That is 400 millivolt. I have written that expression here. Now see carefully. When this resistance is same as this and this resistance is same as this, the output voltage of the circuit is nothing but RF by R1 into V2 minus V1. That is shortcut. RF is this, R1 is this, R1 is this, RF is this. So when this resistance is same as this and this resistance is same as this, output is nothing but RF by R1 into V2 minus V1. That is the shortest way to find the output. So these are some of the application of difference amplifier. I have already told you when I discussed the theoretical part above. Now The common mode voltage is please see the circuit. The common mode voltage is completely attenuated at the output of differential amplifier shown in the given figure. If this common mode voltage is 0 at the output, then you have to find the relationship. First of all, you should know what is the common mode voltage. So for common mode voltage, both E1 will be equal to E2. So I repeat, for common mode, this E1 is equal to E2, and I will say that is equal to E. Fine. So that is the assumption I will be carrying. But for solving the circuit, procedure remains same. Find the voltage at this node. That will be same as voltage at this node. So apply KCL at this node, you will get the relation, and finally put E1 equal to E2 equal to E. So that is the procedure I have followed. So finally, when I put E1 equal to E2 equal to E in above expression of output voltage, that is in the expression of output voltage, you will get output to be 0. Why? Because when E1 is equal to E2 is equal to, that is known as common mode input, and for common mode input voltage, that is E1 equal to E2 is equal to E, the output of the circuit is 0. Why? Because output is completely attenuated, means output is 0 when E1 is equal to E2, when both of these voltages are same. So I am putting the expression of output voltage to be 0 when E1 is equal to E2 is equal to E. So by putting output voltage equal to 0, we get the condition for attenuating the common mode output, and that is this expression you get here. That is the simplified expression. Fine. Now let us see the next example. For expression for the output voltage, the expression for the output voltage we note in terms of V1 and V2 in the circuit shown in the figure. You have to find the output voltage. Fine. And that is V naught is equal to A1 V1 A2 V2. That is given to expression of output voltage is given, and you have to find A1 and A2. So you find the output voltage by first find the voltage at this node, apply KCL at this node, you will get output voltage in terms of V1 and V2. So that is the simple procedure we have been following till now. So I am following, find the voltage at node B, then take VB equal to VA, and then apply KCL at node A. You get output in terms of V1 and V2, and we know V0 is given to you, that is A1 V1 A2 V2. So if you take it like this, so what will be A1? 9.9, and what will be A2 by comparing these two values, that is -10. So you get A1 and A2 values of A1 and A2. That was question in engineering services. Fine. So that finishes your examples or questions based on difference amplifier. But there is one important point to be noted here is, in all the cases, what we do, find the voltage at non-inverting terminal and then apply KCL at inverting terminal to find the output voltage of the circuit, or to find any condition asked for in the question. So that finishes your difference amplifier. So in next video, we'll be talking about summing amplifier. So wait for next video. Thank you very much for watching the video.